So you might recognize this. This is a Cybertruck frame or skin, and this is a design that some people love, some people hate. Uh, who knows what category you're in, but some people may not realize that part of the reason for this design actually has to do with the processing and the manufacturing of it. The Cybertruck uses an ultra hard cold rolled stainless steel that's difficult to shape, hence the very flat structures, but it's very strong and it reduces some of the costs associated with tooling, and it allows you to use this sort of skin as a big structural component rather than um, needing some of that internally. That's not the whole story though. It's corrosion resistant, but you may need some coatings and special care depending on the environmental conditions. And so we'll see these trade-offs between different properties for different materials applications as well. You have glass for phones. Gorilla Glass is becoming increasingly scratch resistant, drop resistant, thinner. Nissan had a battery that was a 24 kilowatt hour battery. And this worked pretty well, over the course of 7 years, you might get around a 25, 28% drop in the ability for the battery to retain its charge. But they switched to a 30 kilowatt hour battery, and suddenly within 2 years, you were getting 15% loss. By contrast, Tesla's battery packs have shown about 10% capacity lost after, say, 200,000 miles. So we can get a really dramatic difference, and we can see the importance of the materials that are making up some of this. And then so there's some other considerations like temperature management that also come into play for these batteries. So we need even better materials. We need better photoresist for transistors. We need better silicon for solar cells, better electrolytes for batteries, molecules for drugs, and polymers for filtration systems, and many, many other applications. New technology is often limited by the materials that are available, not just how we put them together. So as particularly BYU engineers or just engineers in general that will go forth serving, making things in the real world, material science is something that can help you have better things to make those things with. So this class, Science of Engineering Materials, aka Material Science, we're going to talk about three things in this first video. So first is, what is material science? Second, what will we learn? And third, how will we learn about it? So let's start off. Here's a definition from Rustam Roy. Material science is a syncretic discipline hybridizing metallurgy, ceramics, solid-state physics, and chemistry. I think syncretic is probably a word most people don't know or are unfamiliar with. This is an example of where instead of dividing something further into sub disciplines, we've actually got a fusion. So he says it is the first example of a new academic discipline emerging by fusion rather than fission. And so here we have a field that takes a little bit and has elements and incorporates a lot from a lot of different fields altogether. And if we understand these relationships between a material's structure, the properties, and their processing conditions, we can exploit them for better performance. We can use them to design products for for the end use applications. So here we have the material science tetrahedron, and we can see those connections between processing and structure and properties and performance. And then in the middle, we have characterization, which is necessary to quantify and to measure all of these different pieces together. So let's start off with an example. Here we have an industrial cold roller, and this, you take, say, a sheet of stainless steel and you pass it through these rollers that are compressing it. And we're often industrially using multiple passes and going from larger thicknesses to smaller thicknesses. As the amount of cold rolling processing, this processing step, as that increases, the microstructure changes dramatically. So on the top left, we can see at 0% cold rolling, your sort of initial stainless steel sheet, we have the microstructure there. To give you perspective on the length scales, here we have a human hair. This is all the pictures here for the microstructure in the hair. Those are to scale. And so if we take a look at increasing the cold rolling gradually, we see these dramatic differences in this optical microscope image of the structure. We're seeing different phases of materials, which we'll talk about later in the semester, like martensite and austenite, and some really dramatic changes here. Now, though changing the microstructure here affects the properties in turn. So going from 0% cold rolling up to 70% in this case, if we look at hardness, for example, we could go from a Vickers hardness of 174. The absolute value doesn't need to mean much, but just thinking of it like, oh, you would measure the hardness of diamond or soft materials. Vickers is a particular type of hardness measurement. We see that increase all the way to 532. So when we talk about the Cybertruck and it's ultra hard cold rolled stainless steel, we've seen a massive increase due to that cold rolling. With yield strength, the point at which the I guess the sort of the strength of material before it deforms permanently, the sort of linear region of the material before it yields, again, like permanently deforms, that goes from 281 megapascals all the way up to around 1600 megapascals. Now on the flip side, elongation of fraction, which is, let's say you take a material and you stretch it, there comes a point at which it fractures or breaks, with a stainless steel, for example. And the percentage of sort of increase in that, think about the distance, the displacement, that percentage of elongation, the point at which it breaks, that's what we call elongation of fracture. In the initial non-cold rolled state, that's about 52% for this particular stainless steel, this article. And then once we've done 70% cold rolling, it drops all the way down to 1.2%. So you take this cold rolled steel and you pull it apart by 1.2% and it's fractured. So we get this trade-off in different properties, and we see that the relationship between our processing, our structure, and our properties affect those. And these properties in combination affect the performance of the end user application. So here we actually have a Tesla where someone took a Tommy gun, kind of Al Capone style, and kind of raised and rastered bullets onto the side of this. And so this would be more on the form of performance, something that's end use. So again, if we can understand the material structure, property, processing relationships, we can exploit them to enhance performance. We can also discover new materials, not just use and leverage existing ones through a variety of different methods. Sometimes these come from mistakes, like with Donald Stuckey discovering this thermal shock resistant ceramic glass. In his words, when he took this, this furnace accidentally got up to a much higher temperature, he rushed to get it, it dropped on the floor, and he said the thing bounced and didn't break. This ended up being used in ceramic cookware as well as even in rocket nose cones. Same thing with the discovery of vulcanized rubber. The scientist, actually sold his children's textbooks to try to fund his research and was using his home cookware for it. I don't recommend that. But he had a bottle of sulfur that accidentally spilled and tipped over and went into his mixture, and that's actually how we have vulcanized rubber used in virtually every car, very widely used material there. Sometimes it comes through patience, like with the incandescent light bulb or alkaline batteries. Sometimes through serendipitous discovery. The discovery of Teflon was actually when a gas cylinder in a particular laboratory stopped flowing gas, and they took a closer look. They sort of saw this open, found this white powdery substance inside. Other times it comes from attention to detail, like with stainless steel. There was a cannon maker that noticed a shiny piece of metal in what was almost always this big rusted bucket of waste, took a closer look at that. Similarly with shape memory alloys. Sometimes this comes from inspiration, nature-inspired designs like with Velcro, and perhaps my favorite, unsafe lab practices. The discovery of sweet and low, we have a scientist who was eating lunch, a sandwich or something, and he tasted this really sweet sensation on his fingers. And so he rushes back into the laboratory and starts taste testing all these vials of tar-based substances until he finds the one that produced that taste. Definitely don't do that, but that was how we got kind of this artificial sweetener discovery with sweet and low. And we've now entered an age where we're using AI and automation to accelerate the scientific discovery process. This can help improve efficiency, time to results, reproducibility. Here we have the world's brightest molecule discovered as a result of this autonomous experimentation where we're using machine learning algorithms to suggest our next experiments, and we're using robotics automation to be able to carry those out autonomously. And in this case, only a few dozen of these materials had been discovered, and state of the art, best in the world, and many other state of the art ones were discovered in just a few months from this. We can see some other examples here. So there's this organic dye laser molecule, really important for some different quantum research applications. In the middle, we have stronger, more sustainable concrete coming out of a collaboration between Meta and Amrise and academic collaboration. On the right, we have the world's strongest shock absorber geometry. And so this was actually the result of 25,000 experiments conducted autonomously over the course of 3 years. And they were able to achieve this 3D printed structure that exhibited the greatest shock absorbance there. This would be important for like helmets or different army applications, for example. Taking a closer look at the sustainable concrete, these are very expensive experiments. Experiments themselves can be very expensive. There's always some bigger fish, a higher fidelity measurement, things like clinical trials versus testing something at the lab scale on a drug. It took Meta, Amrise, and the University of Illinois 6 months to run 6 iterations. So it was about a month per iteration or batch of experiments. And we see them going from sort of human design batch and progressively optimizing using a tool called Bayesian optimization to increase this optimal trade-off between your final strength. You have to wait 28 days for it to cure, test its final strength, and a sustainability metric. And so they're actually finding some state-of-the-art and high-performing material compositions and processing parameters for these concrete batches. And efforts paid off here. Here we have an image of the concrete that was laid at the actual data center for this. Now, we talked a little bit about the AI piece for discovery, and maybe you're not super passionate and won't end up being a material scientist, but you may find that you have a passion for the impact that some of these materials can play, and you can also realize that there are so many engineering challenges that come into play while trying to build these autonomous systems. So we can see a few examples. We have these lateral moving scarab-based robots. We get into some different robotic solutions. And this next one, we can see a flow chemistry, kind of using high pressure valves and sort of one-way movement. And this next one, we get into 6-axis robotics, arbitrarily moving items from point A to point B. And this next one, try to count the number of tubes. We end up with these very complex sort of liquid-based transfer setups. And in this case, what was referred to as a mobile robot chemist, we have a robot on wheels navigating the laboratory. Perhaps my favorite example comes from Liverpool. We have a dual-armed robot unscrewing vial caps and passing these samples over to a robot on wheels, which then navigates its way over to an X-ray diffraction machine, which we'll also get into later in the semester. It's highly sped up, by the way. We get over there, we calibrate our position, we open one door, we open the next door, we move a little bit closer, we calibrate again to perform this next movement where we grab our samples and load them into the XRD machine. Now, we can't forget, we need to close the door, so we calibrate, close one door, close the next door. So there's a lot of really interesting and complex challenges that can come in this space. And so having engineers, and especially mechanical engineers in this case, participate in that can be really crucial, really impactful. So we talked a little bit about what material science is. Let's talk about what we'll learn during this course specifically. So here are a series of learning outcomes or learning objectives. Anytime you see something like, by the end of this semester, you will be able to blank. That's a learning outcome, that's a learning objective. In this case, by the end of the semester, you will be able to describe the functional behaviors of the primary classes of materials, which are metals, ceramics, polymers, and composites. Each have very different characteristics, oftentimes different applications for them, and they're often used in combination with each other for the final products. So we look at the behaviors of those classes of materials. By the end of the semester, you will be able to predict material properties based on atomic structure and defects. So we took these two cases, let's say we had the atoms arranged in this way, and let's say we were arbitrarily able to grab two sort of sheets of atoms and move them to the right. Which one, case one or case two, which would be easier to move those slabs of atoms across? If we take a look at it, the one on the top kind of have these deeper grooves. If you think of driving, if you had potholes every other, every 6 feet or so, that's going to be harder to make your way through than if you have a nice smooth road. And so that's what we actually see here. As it's moving across, it's easier with these sort of shorter, kind of less, not so deep aspects there. And as we introduce defects, that also affects a lot of the properties. So this is just a very basic example of how we might see atomic structure affecting some sort of final mechanical property. By the end of the semester, you'll be able to apply the lever rule to binary phase diagrams. The lever rule is something that helps you find relative amounts of two phases, like a solid or a liquid, in equilibrium at a specific temperature and overall composition. This sort of chocolate binary phase diagram, I think comes from the 1950s, and we have the percentage of chocolate on the x-axis, versus vanilla content, and we have the temperature on the top. So if you look at the very top there, we've got hot chocolate, but notice there that it's not just some flat straight line. We actually get that the point at which the entire mixture is all liquid actually depends on not only the temperature, but also the percentage of chocolate in there. And so you'll end up with different phases, like a vanilla malt plus the chocolate, or a chocolate malt plus the chocolate, or this kind of pure vanilla solution, vanilla plus chocolate ripple. I still want to know what a chocolate ripple actually means. I couldn't figure it out. So let me know if you do. So this is the lever rule, and this is an example of a binary phase diagram. So we'll be able to do that for various material systems by the end of the semester. By the end of the semester, you'll be able to model the stress-strain diagram and describe mechanisms for altering this stress-strain relationship for various classes of materials. So here on the left, if we take a look at a stress-strain test, we have what's called a tensile specimen being gripped on by a machine that will then pull it apart. And so we're performing this tensile pulling test. So we take a look at that, the sped up version, and at some point as we're stretching it, it breaks right there. If we take a look at this, so we have the stress on the y-axis, the strain, stress in megapascals, strain in percentage. And if you think about it, in this system, you're measuring two things. One is the actual displacement. So as you're pulling it, you want to know the displacement. That gives you the strain or the percentage increasing. And then you also want to measure the sort of the stress or the force required in order to pull this apart. So you're measuring both of those simultaneously. And during the duration of this test, you might get something like this. This would be a more characteristic curve for a metal, for example. And we have the starting, before it's been pulled apart, and then the final one where it's actually broken. So the yield strength, which we talked about a little bit earlier, this would be this region where it's linear, and past that region, you're now deforming the material permanently. It's not going to go back to its original state. And over here, we have the elongation of fracture in percentage, which is where the test more or less ends, is that it's now broken. You've kind of rapidly, the stress required is now no more because the thing has, the sample itself has broken apart. Okay. Also, by the end of the semester, you'll be able to describe the kinetics of diffusion and the process of nucleation and growth as they affect transformation products. So just because kind of a fun example here, we won't necessarily be studying snowflakes, but an example of nucleation and something that can help us with other forms of that here. We see some ice crystals nucleating, going from a liquid to a solid phase. And if you look at the internal structure of ice crystals, you'll see this sort of hexagonal structure forming there. And so it's kind of a nice snowflake example here for diffusion and nucleation and growth. And we'll be looking at that for various systems and how that plays out. By the end of the semester, you'll also be able to describe common degradation and failure processes for each basic class of materials. So if you've ever had silly putty and you hold it up, you might notice that it slowly creeps down. That's something you find more characteristic of polymers. You also find that at higher temperatures for different things like jet engine turbines, for example. You can still get creep, but each class of materials and each material will have its own common ways that it fails or degrades, and we're going to learn about those for, again, metals, ceramics, polymers, composites, and have some real world examples where we're calculating things for those. You'll also be able to identify functional requirements for real world scenarios and select a material based on those requirements. And that's also going to include some other things like economic, environmental, and societal impacts. So as engineers, with these real world scenarios, how do you leverage material science and the choice of material to help meet the needs of the application? And then finally, these two, they're less about material science and more about the general process here. Document materials data in publication quality graphical and tabular forms, discuss the meaning of the data, so analysis, and then develop engineering problem statements for real world materials problems using what's called the BYU ME problem solving process, which came about, as I understand it, from feedback from employers of BYU students, years after their graduation, of things that were strengths of BYU students and other things that they valued and wanted to see. And so this is not to make life harder, but to kind of help prepare you for industry. All right. So we talked about what material science is, what we're going to learn in this class. Now let's talk a little bit about how we're going to learn that this semester. And so this is really specific to ME 250 here at BYU. Exams are heavily weighted in the course, 63.2%. You can see Learning Suite will have 3 midterms and 1 final, and these are mostly non-cumulative, meaning exam 1 covers this amount of material, this portion of material. Exam 2 covers this next portion, 3, 4, and for the final. There's obviously going to be some overlap between concepts and some things, but on the large part, it's not cumulative in that sense. Group projects will be 11.6%. These are due on Saturdays. This is really about a real world application where you're going to select an application, identify the current material that's being used in that one, and do some design with alternatives based on those functional requirements that you've identified. This lasts the full semester. Around week 5 is when groups will form, so there'll be some individual assignments leading up to that, at which point, about week 5 and on, you have the full, sort of this full group project together for it. Labs are 10.5%. We have 4 of these. These are due, the write-ups are due on Friday. You'll sign up. These aren't scheduled. We have these 2-week windows in which you can sign up for particular slots. And these are great. You'll be testing and analyzing real materials. So for example, running a tensile test, taking something and heat treating it in different ways. So take like a red hot, aluminum or steel tensile specimen and quenching it in oil or water, or air, and seeing how that affects the stress strain curve and the different mechanical properties. So various labs like that. I think they'll be interesting and meaningful, a lot of fun. Homework, 10.5%. These are due on Wednesdays. And you'll find that a couple ways. So Learning Suite has the syllabus, the schedule. You'll get links to Wiley Plus, which has the e-textbook, as well as the online homework. That's sort of the core piece of the homework there. In addition to, and the textbook and the homework, those are sort of inseparable. So one of the key things you'll be doing as a BYU ME 250 student is signing up for Wiley Plus, getting that. We also have the SAFER method, which is this BYU developed sort of template or structure for going through some of these problems. And there will be specific problems that are designated as SAFER problems, where in addition to solving and answering the problem, you'll also have this sort of more formal write-up, which you can download the safer PDF and annotate it, by hand or on the computer, but just following that sort of format. And then we have class quizzes at the beginning, typically, that are worth 0.5% of the overall grade. And these are based on the reading. So the expectation is that you'll do the reading prior to class and be able to answer some of these quizzes. We'll be using something called YPoll for that. Then there's some extra credit. We have student ratings. You know, it'd be awesome for everyone to include these student ratings. Uh, it'd be great also if I could get some feedback, during the semester too, to help improve. But just by virtue of submitting those, it's 1%. And then we also have a service one. So this involves, maybe something you're already doing or something you would like to do to help to support somebody else. Do a small write-up on that. That can be an extra percentage in the grade. So here we have, this is a course taught at Brigham Young University. We have the honor code, which involves not only things like dress and grooming standards, but also academic honesty. And we're in 2026 now. This is an age where generative AI is really playing a critical role in a lot of applications for better or worse. And this is something that many instructors and students as well are grappling with. And so for this particular course, and again, just for this course, this doesn't apply for other ones. That depends on their syllabi, their procedures, and what they outline. But for this one, I had this class where somebody said, "Oh, there's no way to." The professor said, "You can't cheat in this class." And I was like, "What?" Like, but you can plagiarize. And the main thing here is, who did the work, where should the credit be ascribed to? And so I'm sure many people are using and will continue to use generative AI models, large language models, for various things. I use it all the time in my own research on autonomous experimentation that I talked about earlier. I use it plenty for code development. And these can be really powerful tools, but they can also take away from some of the learning experience and opportunities. Even some of these big names and large language models, they'll talk about cases where it might make sense to use some of these tools and cases where it won't. And one of those is if you're trying to learn and study, misuse of that can actually prevent you from kind of having that meaningful study there. So my main ask here, my ask is that for any usage of tools like this, that you include the transcript for that. So there's almost always a share link, or you can, like print a PDF or something like that. But usually there's a share link to a transcript, and that's going to provide provenance and sort of a history of your thought process, and seeing that communication, between you and this model, that's important in itself. So it's kind of like, who do we ascribe the points to? Who's the one doing the research? I'd rather not give ChatGPT an A. I'd rather give you a grade that reflects your own work and what you're putting in, and that as you are using external, other resources, that you're, like including a share link and a kind of a provenant kind of history of that as well. So we'll kind of wrap it up here with a guided inquiry. We have these three materials, or three products actually, on the bottom. So we have an airplane wing, we have a spark plug, and we have a soda bottle. And so this is something, if you want to pause the video and take some time for yourself, just kind of write out for each of these. For an airplane wing, what is the intended function and what are the requirements for this? What properties or needs must each material fulfill? And then what type of material or materials are used in this? Again, thinking like metal, ceramic, polymer, composite. And so when we think about an airplane wing, for example, well, what's the function of it? Well, we need to generate lift. So how does that happen? It's with the shape, but in order to do that, it needs to be able to resist those forces that might otherwise break it as we're trying to get lift. Now, at the same time, we need it to be lightweight. Heavy things can't fly, as well as lighter things, and so this is another, where the weight of it, and maintaining both the weight and the structural integrity of it is very important there. So then we can start talking about specific properties and needs in terms of like deformation characteristics, uh, restrictions on the allowable weight. We also we don't want the airplane wing to snap off. Hard to fly an airplane with just one out of two wings. And then just talking about the materials a little bit, oftentimes we're using aluminum, different aluminum alloys. Next for spark plugs, here we actually have a mixture of ceramic and conductors. So we want electricity to conduct where we want it to and not where we don't want it to in this car. And so for this particular spark plug, or just spark plugs in general, you'll have conductive metal through the center. Maybe it could be copper or some kind of steel, and then the ceramic insulator around it. Now let's jump to the far right with the soda bottle. This is kind of an interesting one. You want it to be cheap, right? Like cost is a pretty important concern there. You want oftentimes you'll want it to be transparent. So now we're getting into optical properties rather than just mechanical or electrical. And another interesting one, soda is carbonated, Johnny. So we have carbonated beverages that uh, have a certain pressure, and we actually want that carbonation to stay there. We want the carbon dioxide to not go through the plastic, and so we get into ideas of diffusion, diffusivity, and that also comes into play with the thickness of the soda bottle, which then the thicker it is, the heavier and more costly it is, and so we get all these trade-offs as well. So I encourage you to think about these applications, think about some applications that are important to you, and look at what's the intended function, what are the requirements, what are the properties that needs to be fulfilled, what are the types of materials that are often used, and this will help you, especially for the group project and just in general with your relationship and approach for material science. How do we choose the best material for a particular application in the real world? So, science of engineering materials, aka materials science. We talked about what material science is, this sort of synergy of many different fields that's focused on structure, processing, property relationships to help us design better performing materials. We talked about some of the different things we'll learn, like the lever rule for binary phase diagrams, stress strain curves. And then we also talked about how we're going to learn about this at BYU in this particular class. So I look forward to the semester and for learning together about how exciting and how impactful and relevant material science can be.